What's up, YouTube? I'm back. And this is like the third take now. I'm really suck at, planning. Anyway, last time in part, I think, was it 6? I think it was part 6. Maybe it was part 7. I don't remember. No, it was part 6. We talked about makefiles and how to make them, write them, why they're useful, that kind of stuff. It was kind of a filler episode, so was the one before it. But this time, in part 7 of our N-part series on low-level operating system development, we're going to create a function that prints out a hexadecimal value. And it's just going to be one word, so 2 bytes. And that's about it. So let's go ahead and take a look at what we've got. We can see our makefile there. I already went ahead and added the printH method that we're about to create into the dependency list for main.bin. So now every time printH changes main.bin, it will see, hey, we need to update, and it will update and compile. So we're also going to use our printf function to assist us in printing out the characters for our hex code, or our hex word. So without further ado, let's create a printH program here, and let's make the let's make the printH label and get started. So when we print out a when we look at a hexadecimal character, what do we look at, or what are we going to want to print out? I don't know about you. You can do this any way you like. But when I think of a hex character, whenever I see 0x something or other, that to me says it's a hexadecimal character. So 0x anything is a hexadecimal character notation. So we're going to go ahead and create a pattern to follow called hex pattern. Create it like you would any string, and we're going to go ahead and 0x star 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 star, and it's followed by 0 x 0a 0x 0d and 0. Alright, and that is kind of the template we're going to use when we create our string character, or string from our hex number. So if we go ahead and just try to print that out now, if we let's move into ASCII hex pattern, and then call printf, and then let's come down here and oopsies, red. Okay, return. And let's go ahead and make it. Well, no, let me open up main.asm first. Now make it and make run. Oh, whoops, forgot. We need to call our printx method and our main method. Anyway, I opened up main for some reason. Alright, so I've already included it. I got rid of the jump to the second sector, so we're not going to be doing that. Now we don't have anything passed in, so we'll just say call printH. Make run. There we go. Okay, so we've got 0x star 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 star, and that's just printing our hex pattern. I encourage you, by the way, if you're just kind of developing on your own, to do this sort of stuff, because it's difficult getting feedback in assembly when you're programming a boot sector, and you want as much feedback as you can get, so you know where exactly you go wrong when you're programming. Don't wait all till the last minute. That's just good practice. But anyway, we were expecting that. That's what we got. Whoopee. So now, if we look at hex pattern, we can see, okay, well, the 0, 1, 2, the second spot, or the second index of our hex pattern string, is where our first number is going to be. So let's go ahead and say that our argument register for printH is the DX register. So, whoops. So we're just going to make a copy of DX by moving it into BX. So that way DX doesn't change and we can manipulate BX however we like without getting rid of the original data. Alright. So how are we going to get, let's say we have 1, 2, 3, 4 as our hex value. How are we going to get this 1 to be in that spot right there? Or, you know, you get the idea, that spot. Well, the answer is in the command SHR, which stands for shift right. And what that is it's a bit shift. So it will shift the bits of this number right, a specified number of bits. And when it goes outside of the size of whatever register you're working in, then it just truncates. So what we can do is we can shift right our BX register, shift right our BX register 12 bits. And the reason is because we are only printing out one word, which is 2 bytes, and so that's a byte. So that means that each character that we will want to print is 2 bits. And the reason we want to print or shift 12 is because we want this 1 spot to move over to this 4 spot. So we only want it to move over 3 spaces. We want it to move from 1 to 3. And 3, oh sorry, no, it's 4 bits, it's not 2 bits. I was like, what's going on? Yeah, no, a byte is 8 bits. Half a byte, which is what each character is 4 bits. So that's 4, 8, 12. Yeah, 12 bits. I'm right. Alright. Almost had a brain fart there. Okay. So what this does is it takes the first character or number, digit, in our hex number and puts it in the ones spot, effectively. And then we can, if you noticed or remember, this was the second spot in our hex pattern. So all we have to do now is insert the low byte, which would be the low 8 bits of our BX register, into that spot. So to do that, we'll just simply say move hex pattern plus 2 BL. So we're going to, remember these square brackets mean memory location. So move BL into the memory location of hex pattern plus 2. So if we go ahead and take a look at what that does for us, first we're going to have to move a value into DX. So let's just do 0x1234. Whoops. Oh, at the top. There we go. Make run. So we get something. Not sure exactly what it is. Oh, right. But, yeah, something's printed there. Not sure what it is, though. Why is that? Well, if you think about it critically a little bit, what we've done is we've simply moved a 1 into that spot. So it's not inserting a 1 as a character into that spot, it's inserting a 1 as just raw data into that spot. And there is a thing called an ASCII chart that tells us what character is represented by a certain byte of code. And as it turns out, this character is what 0x01 represents. So we need to figure out what the character code for 0 or for 1 is, and then map that to 0x01. So there's a couple ways we could do this, but we're going to just do it one way for the sake of simplicity. Well, let's get rid of that. We'll just do it one way for the sake of simplicity. We're going to go ahead and create a table of hex values. So we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay. We probably don't need that 0 there because we're not reading it like a string. So what we've done here now is, instead of moving BL there, now we can adjust the value of BL to represent that character code, or that character. So we can, so the way we're going to do this is we're going to move, or we're going to change the value of BX to be the memory address, or the memory, whatever's stored in the memory location of BL, or BX, plus our hex table pointer, in a way. So if it was 0, it'd be 0 plus hex table pointer, which would point us to 0. If it's 1, it would be 1 plus hex table pointer, which would point us to 1. And so on and so forth. If it's A, then it's going to point us to A. So to do that, we'll move BX to BX plus hex table. And now let's see what result we get. Whoops. Okay. There we go. We get a 1. So does this make sense how this works? Another way you could do it is you could simply add a value to BX to get you to the right location in your ASCII table. So since all of the numbers are located in successive order, you can do that. So instead of this, I'll just go ahead and comment this out real quick. One thing you could do is you could just say add to BX. It turns out that the ASCII character, or the ASCII code for 1 is 49. So we're going to add 48. And this should do the exact same thing. Let's get rid of that. Oh, right. I commented the wrong thing out. What a dingbat. Okay, let's uncomment that and comment that. And actually I have the order wrong there as well. We're going to have to put this up here. Wow, not thinking there. Alright, add BX 48. Okay, now let's try it. Why do I keep minimizing that? Get rid of Kimu. There we go. Alright, so it does the exact same thing. The only, the difference between the two is I would suggest you don't use this method, because while it works, it kind of works by accident in a way. Just pretend that, I mean, they weren't in successive order for some reason. So like 1 might have an ASCII code of 49, but say like 2 has an ASCII code of 50. Or, wow, that worked real well. 51, there we go, not successive order. Then you'd be like SOL. So you'd have to come up with a different way, and that different way would be this way. This way is just a little bit more universal. It kind of works better. Might not be the most memory effective, but I think it's the most effective in terms of reusability. So now that we've got our first one printed, let's go ahead and print the second character. So all you have to do is move into BX DX, right? Shift right BX 12. Basically just do, or instead of 12 though, we're going to do 8. Move BX to BX plus hex table. Move hex, wow, hex pattern plus 2 to BL, and we're done, right? Wrong. So there's another small problem that you may or may not have picked up on. When we move, or when we shifted BX right 12 bits, we ended up with our 1 in the 4 spot, right? Well, now we're trying to shift only 2 spots, so 8 bits, so the 2 is in the 4 spot. But you still have a 1 here. So instead of reading 0002, it reads 0012, which means that your BL register is 1, 2, and that's not 2, and it's not going to come up as 2, and your text table translation is going to be way out of whack. So what's the deal with that? How do you get rid of that extra 1? The answer is with something called masking, bit masking. And the easiest way to think about this is with gates. So if you've ever taken a digital logic course, you'll know all about AND gates. AND gates are basically, so you might remember XOR from, I think it was last video, maybe the video before, I don't remember. No, it must have been the video before because it wasn't makefiles and all. XOR said, here, let's just look up a table with AND gates. So AND gate truth table. Okay, with the first one, hopefully it's not a total. Okay, here we go. This works. Let's just zoom in on this. All right. An AND gate says that, you know, if A is false or 1, or I mean false or 0, and B is false or 0, 0. The only way and you're going to get your function here, your AB, asserted is if your A is true or 1 and your B is true or 1. That makes fair enough sense, right? OR gates are similar, except that's not exclusive. So if A is true, it returns true. If B is true, it returns true. That's all. And it's an inclusive OR, so that means that that statement is 100% true. An exclusive OR is A XOR B is true if and only if A is true or B is true. So you got some, yeah, so exclusive OR, that's the truth table. There's different truth tables here. We're concerned about the AND. So what an AND gate does is it only asserts if both values are true. So that allows us to create what I like to call a pass-through. So if you have a series of AND gates here, and you've got here, actually, let me find an example. I've got an example somewhere. Okay, so here's a hex pass-through. This was for a different project that I was doing. These are just ORs. Pretend these were ANDs, okay? Forget the fact that they're ORs. Pretend they're ANDs. And ignore this note then. So you can have your data like we do right here going into your pass-through, and what gets passed through is then completely dependent on the second bit. And the second bit, if this is an AND gate, is false, then we have a false and false, maybe, or a false and true. No matter what you have here, you're going to return false. So if this is off, you pass through nothing. If this is on, however, you pass through effectively whatever is whatever your data is. So if you have a 0 here and this is true, you're still passing through 0 because 0 and 1 is 0. But if you got a 1, then you're passing through 1 if you have the pass-through turned on. So that's the basic idea behind bit masking and why we need to use an AND gate, or we need to use an AND in order to bit mask. So, whoops, back to our assembly code. When we write down a hexadecimal number, F, what does that equal in binary? Because right now, AND is a bitwise operator, just like XOR is. It's not a hexwise operator or anything like that. So when you convert F to binary, you get 1, 1, 1, 1, right? Just like when you convert 2 to binary, you get 0, 0, 1, 0. And 9 in binary is 1, 0, or 1, 0, 0, 1. Well, if you noticed, F is all 1s. So we can think of F as our pass-through enable and 0 as our pass-through disable. So what we can do is we can say AND, we can AND BX with 0x 000f. So what that will do then is it will make everything except for the last 4 bits of BX 0. And then whatever the last 4 bits of BX will be preserved, because 1 and whatever else, something else is whatever something else is equal to. So that's just the basics behind bit masking. So now that we've got that employed, we should be reading R2 instead of, let's see, over here, yeah, R2 instead of a 1, 2, because we've shifted this over 2 spaces, so we have 1, 2, and then we've bit masked off everything except for just the 2, so now we have a 0, 0, 0, 2 here. And when we print it, it will print to the second spot, which is still the first, which will basically override what we already did, so we need to then increase that to the third spot. So make run 1, 0. Something happened there. Let's see. Oh, yeah, no. What happened is I did this out of order. I bit masked before I shifted, because I thought about that real hard. So and bx 0x 00f. Whoops, cancel. Ah, there we go. So 0x12. So now conceivably you can tell how we're going to go ahead and finish this. So I'm going to go ahead and finish it, and I will meet you in 3, 2, 1. Okay, so 3, 2, 1 happened, and here I am. We finished it up, so let's go ahead and make, whoopsies, make run 0x1, 2, 3, 4. Wonderful. So that works extraordinarily well. Now, one thing I challenge you to do, and I'll have this done in the next video, so you can check your work. But one thing I challenge you to do is, it's pretty easy to see here that we're kind of copying and pasting a lot of the same code. So I challenge you to turn this into a loop and to loop through each digit in our hex character, or in our hex number, and print it out. So yeah, I'll have my solution next time, but that's something you should try to do on your own time. See if you can do it. Make the code a little bit simpler and easier to read instead of having to copy and paste this all the time. Anyway, now that we've got that done, we can go ahead and go into our main. Okay. And now we can try to put an address in here. So let's try, leading into the next video, to put in let's try to print out our magic number. Now we could just say 0xA55. That'd be easy enough. But what we want to do is we want to print out a specific the contents of a specific memory location. So where is our magic number located exactly in memory? Well, if you recall back, we had our BIOS load us at a memory location 7C00. So we're going to need 7C00 plus 510, because our magic word, or magic, the magic word, magic number, whatever, is 1 word long. So that's 2 bytes. Thus 512 minus 2 is 510. And that should give us, or that should print out AA55. Alright, and there you go, AA55. That's exactly what we wanted it to do. So now you can hopefully see where we're going to be going with using this as a really valuable tool. And next time we'll talk about the A20 line, what it means. It's going to be more of a history lesson. A20 line is a legacy thing, so a lot of BIOS is kind of correcting for legacy nonsense. But, well, not BIOS, but bootloader stuff is correcting for legacy stuff. So we'll talk about that, and then we'll talk about ways to check to see if your A20 line is enabled or disabled. So stay tuned for that. This has been part 7, I think, creating a print string or a printx function. Yeah, see you in the next one.